entire screen. Okay, we can see your presenter view. So
Great.
screen is yours, please.
Thank you. Hello, I'm Mantas Bacevicius, and today I'll present a class-focused evaluation of deep learning techniques for network intrusion detection. I'm hearing echo of myself somewhere. The goal of the research is because of the ever-growing network of communications in today's digital age, it makes it essential to ensure that our systems and networks are reliably protected. However, traditional methods of intrusion detection also have limitations, which are becoming increasingly apparent against the ever-changing tactics of cyber criminals. The goal of research is to explore the possibility of applying deep learning models given the continuous nature of the data set of classification of all 28 malicious network classes. This study combined two network intrusion detection data sets, CI/CD 2017 and 18. To improve data consistency, we merged similar malicious categories and removed features deemed uninformative. Additionally, we replaced missing values with zeros. This process resulted in a new data set containing 28 distinct network traffic classes and total of more than 19 million entries. It must be noted that both CI/CD DS 2017 and 18 datasets are highly unbalanced. Therefore, the merged dataset is highly unbalanced as well. To address overfitting in the highly unbalanced merged network traffic dataset, we employed several deep learning models. First, a deep autoencoder deep neural network was used to potentially reduce dimensionality and extract relevant features. To examine the DIE-DNN architecture fitness of the dataset, a couple of these models with varying number of DAE layers and DNN layers were constructed. First model consisted of 3 dense layers with size 80, 60, and 80, performing the DAE function with ReLU activation in each layer. Then a single dense layer was added to perform DNN function consisting of 80 neurons, again with ReLU activation function. Lastly, another dense layer was appended for output, this time with sigmoid activation function. Then the architecture of DAE-DNN was modified so that number of DAE function performing layers was changed from 3 to 9 with 80, 70, 40, 30, 25, 30, 40, 70, and 80 layout. Number of DNN layers was also changed from 1 to 3 with 80 neurons each. Activation function stayed the same, ReLU for DAE and DNN layers and sigmoid for output. Last approach was to make a separate DAE-DNN model for each of the malicious class in the dataset. Dataset for each model contained both benign and class-specific malicious data. Model architecture for each class was the same non-expanded DAE-DNN model reviewed in previous section. For time-distributed LSTM model, we've constructed 4 LSTM layers with 195, 125, 125, 195 layout with a repeat factor in the middle. The model was trained with 30 epochs for training dataset. The training dataset was split into 1,280 batches. For time series testing, the dataset was split into 10-minute intervals based on the timestamp field. Gaps in the timeline were filled with previous dataset entry, while data entries in intervals that contain more than 1 entry were removed, leaving only the first recorded malicious entry, if it was registered during the 10-minute period. If not, only the first recorded benign entry was left. The resulting dataset was tested with a Young box test for autocorrelation, as it is visible in the figures. Significant correlation with value less than 0.05 and 99% confidence band identify statistically significant correlation values can be observed only in minority of classes. With brute force web, bot, brute force XSS, SQL injection, infiltration, and DDoS attack, LOIC HTTP. The absence of autocorrelation in other classes, including the benign class, suggests that the data points within these classes are independent of past observations. P-values of more than 0.9 have been observed for such classes as FTP brute force, SSH brute force, DDoS attack, HOIC, and DOS attacks for LoRs. The results of DAE-DNN and extended DAE-DNN model classification with weighted average of 1 score are presented in this table. It is notable that the extended model generally performs better, achieving of 93% of 1 score and 95% for recall value. The split DAE-DNN classification models achieved the best results comparing to the other two models. For results for the remaining class, we can assume that the improved architecture might be an appropriate solution for classifying attacks in this way by creating a class-by-class model. While the DAE-DNN model demonstrated superior classification results overall, a closer examination of 1 score values for individual attack classifiers revealed that the more classes perform better with the simple DAE-DNN model. However, the extended model significant superiority was evident in specific classes, like SSH, Petator, port scan, bot, and etc. So as a comparison, in the bottom, I've presented the F1 score results for the DNN model, as well as extended DAE-DNN model, and F1 score is lower than most of the presented other works, but it is important to note that we classified all of the classes available in the data sets. We did not remove classes that were low performing. And to conclude, the DAE-DNN separate DNN models for each class and LSTM models demonstrate tangible progress in classifying network traffic into 28 distinct attack types. A 66 to 99% F1 score across range across various attack types of certain classes, posing persistent challenges due to limited data availability, while weighted average F1 score was 91% and 93% for DAE-DNN and extended model, respectively. These results underscore the necessity for ongoing refinement and optimization in IDS technologies. That will be all from me.
Thank you very much for your presentation. And we agree with